Hello, everyone, and welcome back to our series on urban energy modeling with Dragonfly. And in this video, I'm going to walk you through the workflows for making use of the OpenDSS connection that exists within the URBANopt SDK. So for those of you who aren't familiar, OpenDSS is a engine that is meant to help evaluate the sizes of various pieces of electrical infrastructure like transformers and electrical power lines. And so we're going to use this over the course of this video to evaluate whether a given electrical infrastructure layout for our district here, our simple 13 building district, will be suitable enough to meet the electrical demands of our, coming from our energy simulation side of things. So first and foremost, in order to do this, we're going to be working from the same sample file that we worked towards creating up to video 11. You can find a link to that in the description. And specifically, I'm going to start to clean up this file a little bit more because there's a lot that we really don't need. I'm not interested in making these EUI graphics for this one, so I'm just going to delete everything that comes after the URBANopt component. And what else? And to be honest, also, I don't really need, I think, all of these extra visualizations that I'm doing down here of the, converting over to Honeybee. We've already kind of understood how to set up our model this way. So, all right, so we're left with just the definition that is, for creating our Dragonfly model, exporting that to Geojson, and simulating that within URBANopt. So, okay, so now that we have this, you guys will see that the way that we actually want to interact with OpenDSS is via this input to the Geojson component that we kind of skipped over in the previous videos. And you'll see that there's an input called electrical network here. And so if you want to be able to use the OpenDSS simulation capabilities within URBANopt, we need to plug in something for this electrical network. And you know what? I see I'm still actually writing out this GeoJSON here because we know we're going to be plugging something new into this component. I'm going to set this to false. Okay, so that's the false. So all right, so this electrical network is actually made to take the output of another Dragonfly component. It's under the Dragonfly 3 energy subtab here. And you'll see actually if you click on the drop down, there are all of these components here that are meant to help you build OpenDSS electrical networks. And so I'm going to drag and drop this first component on the canvas here, this electrical network component. And you'll see actually, so this is meant to basically get plugged straight into the Geojson here. That's a network, and maybe I'll just do that right now. But you'll see the electrical networks are fundamentally composed of three different things. So we have a substation, a single substation, which is basically what provides the electricity directly from those large scale power lines. We have transformers that are going to transform that, basically step down that electricity, that higher voltage electricity, to something that our buildings can consume. And lastly, we have connectors, or those are essentially the power lines that connect everything together. So if you guys go over to the Rhino file that we have been using to create our model here, you'll see there's actually a whole big set of sublayers here labeled electrical. So again, the link to this Rhino file is in the video description here. But if I turn this on, you'll see that I actually already have an electrical network that I want to build and assign to my model here, so I can evaluate how well this will meet the electrical infrastructure demands of our model. So I'm going to start to bring this into Grasshopper here. You'll see first and foremost we have our a single geometry for the substation. I'm turning that on and off here, right? This is our substation. So I'm going to bring this geometry into Grasshopper here just by double clicking and typing, bringing up a native Grasshopper geometry parameter. And I'm going to say set one geometry and just select our substation, our singular substation. And let's see, and the substation, in order to actually make sure that it has the properties of a substation, we have to pass it through a component, pass this geometry through the component. So there's this DF substation component that I'm just going to drag and drop on the canvas here. And really, there's not much that you really need to turn a geometry object into a substation. It just has an optional name. So I'm going to just connect up our geometry here. You'll see we get this substation object out of this, and I can then connect this to the substation input of the electrical network. Okay, so we've got our substation specified. The next thing that we need to do is look at the transformers. And if you go over to the Rhino scene here, we have a whole sublayer for transformers. And if I turn that on and off, you guys can see, right, these 5 objects here, these 5 polygons, or BREPs rather, BREP surfaces, these are what our transformers are. And so you can begin to see actually what the logic is for how you should set up these electrical networks. So everything, all the electricity needs to be sourced from the substation. Then the connectors will go and basically you need to have a transformer, or you usually need to have a transformer before you go and interact with send that electricity to your building objects. Um, but all right, so I'm going to bring in, you'll see actually if I look at each of these transformers, there are properties that are meant to be assigned to them. Like this one is a 75 kilovolt connector. This one's a 100 kilovolt transformer. This one's a 51. So I'm going to make sure that I bring these, I'm going to actually bring these in order. So I'm going to bring in the 100 volt first. I think I have these two 75 kilovolt, and then I have these two 50 kilovolt ones. So I'm going to make sure that I bring in these transformers into Grasshopper in this order. So I'm going to copy paste this geometry parameter component here. I'm going to right click and say set multiple geometries. And importantly, I want to make sure, all right, I select the 100 kilovolt one first, then these two 75 kilovolt ones, and then lastly these 50 kilovolt ones. And then when I hit enter, that'll make sure that I've brought in these transformers in that order. Basically, these 5 transformers, so that they're still following the order from highest kilovolts to lowest kilovolts. And you'll see, so when we go and try and turn these geometries into actual transformer objects for our OpenDSS simulation, let me see, we have a DF transformer component here. Right, so this will take the geometry inputs that we have here, so I can plug those in there. But you'll see that we also need to supply properties, right? So these properties are those, kilovoltage values that you saw me label, the geometry labeled within the Rhino scene there. And so you'll see if you go under the Energy tab, there is a DF Search OpenDSS component. So you'll see that we actually ship, URBANopt and Dragonfly ship with a library of transformer properties already ready to go. And you'll probably notice that these actually align with the various names that we had for these geometries in the Rhino scene here, right? So this is 75 kilovolt PM. Oh, and then we have a 75 kilovolt CT. Ooh, all right, I need to make sure we have a few different properties here for all of these ones. Some are PM, some are yeah. Okay, but I think the way I did it, yeah, so it must be this 100 kilovolt PM followed by this 75 kilovolt PM followed by a 75 kilovolt CT, and then these two. So I just need to make sure that I'm selecting out the right values from this list so that they align with the geometries when I create these transformers. So all right, so first things first, I will pull up a panel and make sure that I have a let's see, transformer dash 100 kVA PM. Right, so I know this is the first one. I'm going to then make this a multi-line data panel so that I can then make sure that I have the other one. So I think the next one that we had was this one, which is, this one is a 75 kilovolt PM. So I'm just going to go into this panel here. I'll copy and paste to make sure that this is 75 kilovolts and that's still PM. And then this was followed, I remember, by 75 kilovolt CT. Right, let me go back and double check. So this is a 75 kilovolt, right, CT. And then I have, let's see, this one is the 50 kilovolt PM, and then lastly a 50 kilovolt CT. So all right, so I'm just gonna copy and paste those. Let's do this. So this is a 50 kilowatt PM and a 50 kilovolt amps, I guess I should say, kVA. And then, yeah, CT. And that looks correct. So now, all right, so I've got 5 values here. I've got 5 geometries. These should be aligned with each other. And when I connect up these properties here, that should ensure that they are assigned correctly to these transformers. I'm getting now those 5 transformer objects coming out of this component, and this is what I can then plug into our electrical network. All right, so we're almost there. We just, there's one last critical type of component that makes up our electrical network, and those are these wires, all of these individual wires that are coming through here. And if I go back to the layers tab, you'll see that I tried to label, organize these various types of electrical wires by their, well, essentially these connectors, I should say. So connectors can have multiple wires inside of them, right? They can carry multiple types of electrical currents through those various connector pathways. So I've tried to organize the different connectors that we have here by their the type of wires that they're carrying, and I've tried to label essentially what these types of wires are in the layer names here. So you'll actually see, if we go back to our df search OpenDSS component and I pull up a panel here, you'll see that these actually correspond with wires that exist within a library that ships with OpenDSS and Dragonfly. Right, so this is actually these kind of various wire names that I have in here are referencing values that exist within this library that we ship. So all right, so if I wanted to go and essentially make a connector for a given set of wires here, all that I would have to do, I can drag and drop this DF electrical connector component on the canvas. And again, we need to bring in some geometries. So the way I'll do this is by copy and pasting our native Grasshopper geometry component. Let's see, I'm going to select this first layer here of values, this first layer. I'm going to right click on the layer and say select objects. And that'll select all of the connectors that have this set of wires. Then I'm going to go over to Grasshopper. I'm going to right click on the geometry parameter component. I'll say set multiple geometries. And that'll bring these geometries into Grasshopper here. And then so next I'm going to connect up these geometries to our electrical connector here. And then lastly, I need to assign the wires. Basically, and wires can be a list of these different types of wires that we have in the library here. So the easy way that I'll do this, because I just labeled these layer names with the wires that I want, I'm going to kind of click on this layer again. I'm going to copy this to my clipboard, and I'm going to pull this up into a panel. So I'm just going to double click the canvas, type double quotes, and hit V, Control V, so that I can paste this into a panel. You'll see that I separated them by semicolons in the layer name. So all that I have to do is just right click on this, change it to multi-line data, and I'm going to change these semicolons and spaces to be just enters, right? Just line breaks. And that'll ensure that I now have a list of wires that are associated with these geometries that I can then plug into the electrical connectors here. Right, and so then I'm going to get electrical connector objects out of this component, and these electrical connectors, right, it'll tell me the number of wires in each one. These can then go up to the connectors here. So I'm going to fast forward to the next section. We have a lot of different types of wires here. That are associated with these different types of electrical connectors. So I'm going to fast forward just to build up the rest of the electrical network, build up these 5 other types of wires that we have here. So I'm going to see you on the other side of this. I'm just going to fast forward so that we don't take up too much time doing this repetitive task in this video. Okay. Okay, so I finished setting up all the various types of electrical connectors that I have here in my model. And I want to now bring all these connectors together into my electrical network. All that I have to do, I just hold down Shift in order to make sure I can connect up multiple inputs to our connectors value here. So I'm going to connect up these connectors with these wires, these ones over here, and these ones here. And then lastly, okay, here we go. So finally, once we've gotten this all together, right, so we have our electrical network is defined by a substation, a bunch of transformers, an electrical connector, and all of these come together into a single electrical network object that we then can assign to our Geojson before we export it off to be able to be simulated by URBANopt. And so Really, so essentially all this, the only kind of rules that you need to follow in order to make sure that everything is connected to each other, I didn't say this earlier, but you need to make sure that all of your electrical connectors need to be touching either another connector and or an object like a substation, a transformer, or a building footprint. So as long as your connectors, are touching that polygon, basically that outline of one of those shapes, the Dragonfly plugin is smart enough to know how to sense that those are actually touching each other and ensure that they're all actually connected up when you send it off to OpenDSS for simulation. So all right, so now that I've done that, now that I know my electrical network's all set up the way that I want it, I'm going to now write out a GeoJSON. And this time you'll actually see the electrical network geometry gets written into the GeoJSON that we have here. And I can go and I can preview this. If I open this GeoJSON in the viewer like we did earlier in the series, you'd be able to see the actual electrical network geometry and all the properties that are assigned to those transformers and connectors and everything. But you can just trust me for now. I think we're good enough. As long as we have our network all set up here, everything's touching each other, and we've assigned the properties correctly, I think we're ready to go and actually simulate now our URBANopt model. And then after we get these results from URBANopt, we're going to use OpenDSS to post-process the results. Oh, but one very important thing. So I'd rather not run the simulation for the entire year because, again, we're mostly just trying to understand like what is going to happen in the worst case scenarios, the worst case peak electrical demand, to make sure that our infrastructure is good enough to handle this. So what I'm going to do is, instead of running our URBANopt simulation for the whole year, I'm going to connect up a run period. And the easy way I can do this is under Ladybug. I can go and grab this an analysis period, an LB analysis period component, and I'm just going to run this file for August because I know that's around when I have the peak electrical demand happening when all the air conditioning systems of these buildings are running. So, all right, so I'm going to connect up 8 as my start month and my end month. I just put that inside a panel by double-clicking the canvas, double quotes, and typing 8. So that's how I did that. And then I connect up the period object that I'm getting out of here to our run period of our simulation. The one other thing that I'm going to do is that really Energy Plus runs by default, or when we run Energy Plus simulations from Dragonfly, we use a default simulation time step of 6 steps per hour. And that's probably a little overkill. OpenDSS, usually it's fine if you just run it with a singular time step per hour, just with one time step. Of course, you can always increase that, if you really want to do a detailed study. But I'm mostly interested in just running a kind of relatively quick simulation here. So I'm just going to double click the canvas and put 1 inside a panel. And I'm going to connect that up for my simulation time step here. Okay. And that'll both make my energy simulation faster because we're only running it for 1 step per hour for the month of August. And you'll see it'll make our OpenDSS simulation more manageable. So I'm just going to set this to true, and I'm going to see you guys on the other side of the simulation where we'll actually take our URBANopt energy results and send them off to OpenDSS. Okay, and actually maybe you guys already sensed that was a very quick simulation because it was only running for a month at a time step of one, a lot faster than what we were running earlier. So great. All right, so now we have this. We can start to actually take our electricity usage results that we're getting out of the energy simulation with URBANopt and Energy Plus and send them off to OpenDSS. So under the 3 Energy tab, you will see that there is a component called Dragonfly Run OpenDSS. And if I drop this onto the canvas, you'll see it's actually not too different in principle from the way that we ran the way that we ran Reopt in the previous video. So we need to connect up our GeoJSON, and importantly, this is how the GeoJSON is essentially how the OpenDSS will know what our electrical infrastructure layout is and what the properties assigned to this electrical infrastructure are. So I'm going to connect up our GeoJSON to the GeoJSON input here. Then we need to connect up our URBANopt scenario, which is basically what points to the results, right? Those electricity demand results that are ultimately going to be used in the OpenDSS simulation. You'll see we can actually connect up a run period here if we had instead ran this simulation for the entire year. But we only want to run the OpenDSS for a subsection of that. You can do that here. But I mean, again, I already set a period here, and the default is just to run for the entire period of the energy simulation. So I think we're fine with that. So all right, we pretty much, oh, the only other thing that we need is to set this Boolean toggle to true to run. So I'm going to bring up a Boolean toggle, and I can connect it to run. But before I go in and hit simulate here, there's actually one very important thing to know about the OpenDSS translation process here. So the way that we're able to run OpenDSS, it's all going to run locally. It's not like REOPT where we're sending something off to an API to go and get results. So there's actually another installation step that we need to do just when we want to run OpenDSS simulations. And you'll see if hovering over the input description here, it says that we need to install Python 3.7 and then run this command from command line, this pip install URBANopt ditto reader. And so this is what's going to allow us essentially to to have the OpenDSS and the converters over to OpenDSS installed on our system. So the way that I'll do this, I mean, I'll give you guys a link to install Python. You're going to have to run an executable, but really Python you can just download from pretty easily from just going to python.org. If you just search Python download, it should bring you to python.org. And the critical one that we want is Python 3.7. So as long as you you download Python 3.7, it's possible that it may work with the later version. I know they're still updating the URBANopt ditto reader that's ultimately sending stuff off to OpenDSS. But for now, I recommend installing the latest Python 3.7. You can download it from there. And then lastly, to make sure that you have the actual OpenDSS converters, we need to bring up a command prompt. And you need to type the command that you see referenced in this component description here, which is just pip install urbanopt-ditto-reader equal 0.3.8. So that's what I'm going to do right now. We're just going to type pip install urbanopt ditto reader equal 0.3.8. Right, and because I already have Python installed on my machine, I know this is going to run. Again, you guys may have to run the executable if you don't already have a system Python installed. And actually, we see I already had it on my machine. If you had not installed the URBANopt ditto reader, though, you would have seen it a whole download screen. It would have taken a longer time on your machine. But long story short, all right, now that we know we have Python, we have the URBANopt ditto reader, now I should be able to set this Boolean toggle to true. And this will actually now take our URBANopt energy simulation results, convert them over to the format that OpenDSS wants, and ultimately is going to run all those results through OpenDSS for the time period that we selected here. And you can actually see, right, it's running through the 1st of August, 2nd of August, 3rd of August, right? It's going to run through the whole month that we did an energy simulation for here. So I'm going to wait for this to finish simulating, and then I'll show you how to parse in the OpenDSS results at the end of this. So I'll see you on the other side of the OpenDSS simulation. Okay, so the OpenDSS simulation finished, and you'll see the outputs that we get from running OpenDSS. If I pull up a panel here, we have a few list of files. It looks like I think they're all CSV files that we get from OpenDSS. But essentially, we have the results for each of our building objects within our model, right? I think we should be able to get voltages and stuff that are associated with those buildings. We have the loading of each of the connectors that we put into our electrical network here, right? And we can see each of those as being labeled with the name or the ID of those electrical connectors. And then lastly, we have the loading that's happening on our transformers here, our 5 transformers in our model. And so all of these results, all of these CSV files can actually be parsed with the same Dragonfly component. If I go and grab this, what do we call it? Read OpenDSS result, and I drag and drop this onto the canvas here, you'll see that we can connect up our list of DSS CSVs, like for example, our building DSS CSVs, and then connect, let's see, looking at the outputs here, we actually can look at the factors. So this should look pretty familiar. These are just data collections for the month of August that have the voltage factors essentially associated with each of these buildings. And then we should have data collections of conditions that tell us whether things are over or under loaded. So the easy way that we can preview this in the Rhino Grasshopper scene and understand exactly what these results are, I can go over to Ladybug and drag and drop this LB hourly plot component on the canvas. And you'll see if I connect up our factors to the data input here, and then I go over to Rhino Grasshopper, we should see, I'm going to go to top view so we can see this a little more easily. We could see the factors for each and every one of these buildings, right? Each of the 13 buildings in our model. And you see that pretty much all the factors are very, very close to 1. I mean, there's obviously some deviation from this, some very slight deviation, but this is actually a great sign. Being close to 1, a factor of 1, is actually, that means that things aren't under voltage or over voltage, right? They're kind of just at the range that we want. And we can go and verify this actually, for all of our buildings, we can verify this by plugging in the condition. And yeah, this is beautiful. This is exactly what we want to see. So all of our buildings have a normal amount of voltage. There's no over voltage or under voltage, right? All the buildings are nicely fitting in that category. Of course, we'd see red or blue if that were not the case. If I were to take the connectors, right, we can look at the same thing, the condition of our connectors, to see if they're overloaded or just normal. And these are all blue, which looks great. Right, but we can actually also see the individual factors, right? We can see uh, all the factors are pretty close to 0, right? Which is again the kind of value that we want to make sure that it's not overloaded in this case. But we do see there's some slight deviations depending upon the electrical demand, the hourly electrical demand here. But again, this is great. This means that our connectors, none of our connectors are overloaded for our model here. Right, that they're all, even though the loading is changing, it's so small that it's not going to cause our lines to be overloaded. And then lastly, we can take a look at these 5 transformers, right? We can see the factors here, and okay, it's looking a little, we're starting to get some factors that are a little bit higher here, right? For the, I guess this should be the loading on the transformers, right? So these are a little far from Unity. Maybe, I don't think they're that far. I mean, I know if you search through the guidelines on OpenDSS, they'll actually give you guidance on what factors are actually at a point that it may be concerning. I think for all of these, let's see, for the conditions, yeah. So for all these conditions, the loading is still low enough that we're not overloading any of the transformers, so that's great. Right, we see the factors are understandably a bit higher than just 0. Which I guess is the perfect amount, but this is still, it seems, within the limits, the design limits of these transformers. So all right, so hopefully this gives you a sense, a sense of how you can use the OpenDSS capabilities that are embedded within URBANopt, and that we essentially ship with Dragonfly. Um, I know, as we were running this video, like there's a very specific version of URBANopt Ditto Reader that I was using in order to make sure that that everything works smoothly. I know the National Renewable Energy Lab continues to update the URBANopt Ditto Reader, and so at a later point, you guys may see the description of this component change if you should use a newer version of URBANopt Ditto Reader because they're constantly improving this. I think maybe in the future too, we'll add more libraries of properties for our transformers and the wires that we ship with Dragonfly to make this a little easier. There are also ways, I should say, of making your own sets of properties. You'd have to do a small amount of Python scripting, maybe like a few lines of Python to be able to do that. But again, I mean, there are ways of doing this. Everything's really fully customizable under the hood because it's all open source and we're all, working with the same set of standards under the hood. So, all right, hopefully this gives you a sense of how to use the OpenDSS workflows, how to test electrical infrastructure with OpenDSS. And thank you guys for joining us through this series. I'm sure that we're going to add more videos onto this, but I think this is a good stopping point for now to give you a pretty good overview of a lot of the things that you can do with urban energy simulation and URBANopt. And thank you again for joining us.